Hi, 5th and 6th grade. We are going on to the next section of science today, which is 12.5, and we are going to be learning about celestial, or stars, interactions. I have Sam, the science cat, here who is going to help me, or wants to learn as well, so he's going to hang out. All right, so we are on page 148 in your science book, Celestial Interactions. So let's start with some vocabulary. Binary star. A system of two stars that revolve around each other. Ellipse is an elongated oval shape. An exoplanet is a planet orbiting a star other than the Earth's star, or the Earth's sun, which is a star. As well as the celestial objects themselves, astronomers also take interest in their movements. Two stars that revolve around one another are called binary stars. These double stars orbit around each other's center of gravity. Interestingly, these may appear like slow pulsars, dimming when one begins to eclipse the other. Sirius A and B are binary stars. Stellar systems with three stars are called triple stars. Proxima Centauri is thought to be part of a triple star system in which Alpha Centauri A and B, binary stars, are the other two companions. Planets orbit the sun in an elliptical path. An ellipse is similar to a flattened circle. Mathematician and astronomer Johannes Kepler was the first one to describe the motion of planets as ellipses. Kepler's calculations led him to formulate the laws of planetary motion. This first law states that the orbit of every planet is an ellipse. Kepler's second law describes the fact that the planets travel faster when close to the sun and slow down when they're farther away. The relationship between a planet's distance from the sun and the time it takes to orbit the sun is explained by his third law. Due to the Earth's daily rotation, stars seem to follow circular arcs. In addition, Earth's yearly orbit causes stars to appear to move across the sky. This apparent motion occurs because the dark side of the Earth faces different directions on its elliptical paths. To know whether stars actually move over time, astronomers compare their movements, not to Earth, but to the sun. Stars change position in the sky only slightly as the decades pass. Such star drifts are known as proper motion. Since the sun itself moves within our galaxy, which also rotates and drifts, stars have very complex paths. For this reason, proper motion is the most practical description. In addition to apparent and proper motion, some stars slightly wobble. Astronomers take special interest in this because wobbles likely result from orbiting planets. Any planet orbiting a star other than the sun is known as an exoplanet or extrasolar planet. With reflect light too dim to detect, these planets are seldom observed directly. Instead, astronomers infer an exoplanet's existence from using mathematics. Since the 1990s, astronomers have detected more than 300 exoplanets, none similar to Earth. And so they've been able to detect other planets moving around other stars other than the sun, way out past our own galaxy. If we look at the pictures and the description boxes around, on page 148, like planets, comets orbit the sun in elliptical paths. A number of years ago, I forget what year it was, I might have been in high school, Halley's Comet was visible over the Earth, and I think the next time it'll be by is like 750 years or something. But it was really fascinating to see and to know that this comet or ball of ice and gas that is caught in an elliptical pattern because of gravitational pull, to think that it's out there orbiting, and it takes like 750 years for it to make a full orbit around the sun. But it was really a neat thing to observe. I remember my dad took me to Salem State College because they have a space observatory on the top of one of their buildings with really high power telescopes. And so they were open to the public to come and use the telescope and look at Halley's Comet through it. And it was amazing. Such a neat thing. So maybe in our lifetime we'll be able to see a new comet or another comet come and grace our skies. Albiero, identified as a binary star, can be viewed with minimal magnification through a telescope. However, astronomers think that the brighter yellow star is itself a binary system, though its stars are too close together to distinguish. So you can see there the two stars are really close together. You have a bigger yellow one and then a smaller bluish white one, and what they think is the yellow one actually might be another binary system in itself. So two stars that are orbiting each other or more, could be a triple. So orbiting themselves, and then that one whitish blue one on the outside is also orbiting it as well. Strange but true. Although this looks somewhat like the moon, it's actually Mercury. Pretty cool. In the field, the North Star, also called Pole Star, is the star that at the northern end of the Earth's axis points to. Egypt's ancient pyramids were aligned to true north. Yet the North Star of that day was Thuban, not Polaris, as it is today. In addition to becoming our present pole star, Polaris has more than doubled in its brightness since that time. Due to proper motion, Polaris will reach its most northerly position in 2017 AD. In about 12,000 years, Virga, located on the constellation of Lyra, will be our most northerly star. So that's pretty fascinating. So 2017, so 3 years ago, is when Polaris met its most northerly position. That's pretty cool. It's within our lifespan here. The swirly picture on the bottom says this time-lapse photo captures the light from the stars during Earth's rotation. It illustrates the apparent circular path of the stars as seen from Earth. And then this image dramatizes, so this is not an actual picture from a telescope, but a computer depicted what they theorize it looks like. This image dramatizes the closest exoplanet ever detected directly. Known as HD 189733b, this planet orbits 30 times closer to its sun than the Earth orbits its own sun. The immense heat from the star-facing side produces enough low-frequency radiation to be detected directly. It's pretty neat. Okay, so when we think about the orbit, we're going to go into our lab book and talk about some theories over the years that scientists had about planets and how they orbited in the solar system and in what shape they orbited. And so we always believed that it was a circular orbit, that they just moved in a perfect circle around the sun, that it had equal gravitational pull. But Kepler found out years later that it's actually elliptical. And so what that looks like when you have an elliptical orbit, let me just come to the board here. With an elliptical orbit, it is more like an oval shape or like an egg shape. So the Earth rotates more in kind of an egg-shaped pattern than a circle. And so if this is the sun, I'll use red for the sun. Okay, here's our sun. Earth is the third planet from the sun, so we are not the closest one in our solar system to orbit the sun. But if we think about our orbit to the sun, instead of what was believed before, let's say this is Earth, that we just moved in a perfect circle, in a year, 365 days it takes for us to go around the sun. Instead of that theory of being circular, Kepler, by using math, actually figured out that it is more of like an elliptical orbit around the sun. So times when we're closer to the sun and times when we are farther away from the sun. And so those different quarters that we have are what we have like our solstice for our season. So you have winter solstice on December 21st, you have summer solstice on June 21st, and then you have spring and autumnal equinoxes. And so you have your spring or vernal equinox, and then you have your autumnal or fall equinox at the other ends. And so fascinating to think that math is actually what helped them realize that the earth moves in an ellipse rather than a circle. And so they also found that all the planets move in an elliptical pattern. Some have a more extreme elliptical pattern, so they might hug the sun and then their orbit goes way, way out past the sun in its orbit. And so for us, it takes 365 days to go around the sun. For other planets, it takes hundreds of years for them to make one revolution or one orbit around the sun. So we're going to go to our lab books now. If you open up your lab book, we're only going to do 12.A today. We're not going to do B. Okay. And so on 12.5A, you have some reading here about analyzing different theories over time of planets and their relationship to the sun. So we're going to read this together, and then there's some questions for you to answer. So read the following paragraphs about several famous astronomers and answer the questions below. In approximately 140 AD, so if you think of this, this is only 140 years after Jesus was on Earth. So 140 AD, the Greek astronomer Ptolemy developed a theory known as the Ptolemaic system. His theory was based on the idea from Hipparchus, who lived from 190 BC to 120 BC, so before Christ, who believed that geocentric or Earth-centered models of the solar system, and Aristotle, who lived from 384 BC to 322 BC, who suggested that the planets had circular orbits. Ptolemy also explained the apparent backward motion of the planets by adding that they, as well as the sun, moved in small circles around larger circles known as epicycles. This theory was widely accepted for 1,500 years. So this was the theory through the time when Jesus was alive, hundreds of years before Jesus was alive, until a couple hundred, or just under 200 years after Jesus was alive. This was the theory that was widely accepted, that they moved in circular orbits, that it was an Earth-centered orbit, which meant that the Earth was in the middle of the solar system and everything else, including the sun, orbited around the Earth. And so move ahead a couple hundred years, more science, more understanding of math and how that relates to the world around us, we see some new theories popping up. Polish astronomer Nicholas Copernicus renewed a theory in 1543 that Aristarchus, a Greek astronomer, had first introduced sometime before 230 BC. They believed in a heliocentric or sun-centered model. So meaning that the sun is actually the center of the solar system and all planets orbit the sun. So this understanding, this heliocentric or sun-centered model, astronomers, Aristarchus believed this in 230 BC, when it was widely accepted that it was a geocentric or an Earth-centered solar system. So his theories were probably widely disagreed with because most people believed that the Earth was the center of the universe and of our solar system. But revisiting this years later, you have new scientists, Copernicus, coming out and saying, he might have been onto something. Copernicus advanced the idea that the orbits of the planets were concentric circles, a nest of circles within larger circles. So if you think of like ripples on water, if you throw a rock into a pond, you have ripples that go out from that center point. Those are concentric circles, like a target. Okay, they're not overlapping. They move from smallest and they get bigger and bigger and bigger and bigger as you go out. And those are concentric circles. And so they believed that the planets move in concentric circles. Okay. Ptolemy's idea of epicycles was also adapted by Copernicus. People were hesitant to accept the heliocentric system until Galileo, 1564 AD to 1642 AD, collected enough evidence that convinced them that this was valid. About a half a century later, so about 50 years later, Johannes Kepler analyzed some observations by Tycho Brahe, 1546 to 1602 AD. He first assumed circular orbits, but soon found that his calculations did not fit the observations. Kepler eventually discovered that orbits were elliptical in shape. So little by little, over hundreds of years, we see that scientists have been able to, through math, through science, through better research and development of telescopes, to really start understanding what is outside our own atmosphere. So some questions to answer about these early astronomers. 1, was any part of Ptolemy's theory correct? Explain. So parts of his theory were the geocentric or Earth-centered model. Did that end up being correct? Another thought of his was circular orbits, that the planets moved in circular orbits. Was that one correct or proven correct? And he also believed in epicycles. So epicycles, we'll go back up to the first paragraph. It said they moved in small circles around larger circles, known as epicycles. So was that proven correct or not? Number 2, what idea did Copernicus have that was later found to be true? Okay, so you can go back, and so Copernicus looked back at Aristarchus, and what did Aristarchus believe in 2030 BC that most other scientists did not believe in? What beliefs of his were not true? And so Copernicus, what did he believe at first and proved that it was not true? Of the astronomers mentioned, who first suggested the geocentric model? So look way back, and who was the first one to base an idea that they were geocentric, Earth-centered? Of the astronomers mentioned, who suggested that the sun was the center of the solar system? So the heliocentric. Who proved that the heliocentric model was correct? And then last, what did Kepler determine? So this has to do with the orbits. What did Kepler determine the orbit of the planets is around the sun? All right. If you get a chance, hop onto YouTube, go onto NASA or National Geographic, and watch a video on planetary orbits around the sun. And see if you can do some research information on, we know our orbit, we know our Earth revolves, so it turns on its own axis one time every 24.6 or whatever the point is, hours. So every day, the Earth rotates completely on its axis, but every year, every 365 days, we go all the way around the sun. Now, other planets have longer orbits, and some have shorter orbits. And so see if you can do some research, watch some educational videos on that, because it's really fascinating to see our relationship to other planets and all of our relationship to the sun and how we orbit. You do not need to do 12 6.5b in your lab book, so you can leave that blank. And then next time we're going to be going on to the next part about stars, where we're going to start talking about constellations. If you've ever been stargazing, you can see sometimes stars and the way that they're placed in the sky look like they form kind of a picture. It's like looking at clouds and seeing pictures in the clouds. But we're going to be talking about clusters of stars and constellations and why constellations were important over the years when it came to astronomy, and why they're neat for us to look at today. And so we will touch on that next time, and I will see you then.